quantum numbers, n. The principal quantum number n. Must be a whole positive number. So n is 1, 2, 3, and so on. That's the principal quantum number. The secondary quantum number, L, which is also the types of orbitals, follows the rules from 0 up until n minus 1. So if n is 1, L can only be 0. If n is 2, L can be 0 and 1, because n minus 1, 2 minus 1 is 1. If n is 3, if the principal quantum number is 3, L can be 0, 1, or 2. So what does this mean in terms of types of orbitals? If L is 0, we have an s orbital. It doesn't matter which energy level we're on, it is an s orbital. If L is 1, these are p orbitals, and if we are L equals 2, these are d orbitals. So, on our energy level 1, on our first energy level, we've only got one type of orbital, and it is the 1s orbital. The second energy level has two types of orbitals. We've got a 2s type and a 2p type. On the third energy level, we have a 3s orbital, we have 3p orbitals, and we have 3d orbitals. So the higher the energy level, the more types of orbitals you have. The third quantum number is the magnetic quantum number, the ml value. And this actually gives you the actual number of orbitals. So this is bound by the rules negative L through 0 up until positive L. So, if L is 0, ml can only be 0. If we are on the 2s level, the n is 2, L is 0, ml has to be 0. If n is 2, L is 1, our values are negative 1, 0, and plus 1. So we have three values. Negative 1 is 1, 0 is another, and plus 1 is our third one. Then for the third energy level, if L is 0, we have 0, L is 1, again negative 1, 0, plus 1. And then for the D, we've got negative 2, negative 1, 0, 1, and 2. So you can see that you have one actual orbital on the first energy level. We have one actual orbital. On the second energy level, we have two types. But we have a total of 4 different orbitals. We've got our 2s orbital, and then we have 3 different p orbitals. So here we go. Actual orbitals. There are 4 possible orbitals on the second energy level. Before we looked at n squared is our actual, well, here is our actual. We have a 2s orbital, and then we have 3, got 1 2s orbitals, but then we have 3 2p orbitals. We have a p in the x-axis, a p in the y-axis, and a p orbital in the z-axis. So there's your n squared actual orbitals. There's your 4 orbitals, an s orbital and 3 p orbitals. Now, if we look at n equals 3, we've got 1 3s orbital, got 1 3s orbital, we've got 3 3p orbitals, and each one of these values is an actual orbital. Each one of those is an actual orbital. So we end up with 5 d orbitals on the third energy level. 5 3d orbitals. So our n squared was 9. And here you go. Here's your 9. 5 plus 3 plus 1 is 9 orbitals. Just look at the 2p orbitals again. So 2p, if we're in the 2p, our n value is 2, our L value is 1, and now we have 3 ml values. ml can equal -1, ml can equal 0, and ml can equal +1. So each of these set of 3 quantum numbers, each of these 3 sets is the address or boundary of an actual p orbital. So your periodic table is actually organized by periodic trends, but also orbitals. This is your S block. This is your P block. This is the D block. And this is the F block. Now, there's 2 elements in the first 2 columns on each row. There are 6 elements in a row in this section. There are 10 elements in a row here and 14 here. Now, there's only one s orbital per level that can hold a maximum of 2 electrons. 2 electrons and 2 elements. The P block, 6 elements. There's 3 p orbitals per energy level or per row. Each can hold 2 electrons for a total of 6 electrons. 6 electrons. D block. There are 5 d orbitals per energy level or per row. Each can fit 2 electrons for a total of 10 electrons. The F block, each row or energy level is 14 elements. There are 7 possible orbitals. There are 7 possible F orbitals. Each can hold 2 electrons for a total of 14 electrons. Coincidence? I don't think so. Hydrogen. This element is on the first row in the S block. So its electron, its one electron, is in the 1s orbital. So the orbital itself is determined by these values, and then the identity of the electron is identified by those 3 plus 1 more, and that would be plus 1/2. So it's spinning clockwise, or spinning up. So this is the 4 quantum numbers that describe the hydrogen electron. The first 3 only describe the orbital, but if you have a 4th one, now you're describing the electron. That electron is in that orbital. Helium has 2 electrons in the first energy level because there's only one orbital, the 1s orbital, on the first energy level. Both of its electrons are in the 1s orbital. So one electron has these as its 4 quantum numbers, and the other electron will have these as its 4 quantum numbers. You'll notice, you'll notice that they only differ by the 4th quantum number, the spin. One will spin up, one will spin down. The first 3 quantum numbers are the same because this identifies the orbital that they are in. They're in the 1s, orbital. No 2 quantum numbers in the same atom can have the same 4 quantum numbers. So, one will spin up, one will spin down. You can have 2 different elements with the same 4 quantum numbers, but they are different atoms. Okay? The same electrons in the same atom will not have the same 4 quantum numbers.